Hello, everyone. Nice to meet you all. My name is Yu Shin, a postdoctoral researcher at KAIST and a co-organizer of this Urban Seminar Series. Today, we are really happy to have you all for our KAIST-NYU Young Research Day. Total of 12 students and young researchers will join us to introduce their fascinating studies within the context of urban artificial intelligence and data science. We really hope to have this opportunity to facilitate the research collaboration between KAIST and NYU for more interesting studies. This is organized as two-day program. Today we will have 4 presentations from NYU and 3 presentations from KAIST. For our first speaker, Rayan Kim from NYU Tandon Engineering School will present his research on building Verisimilitude in VR with high-fidelity local action models, a demonstration supporting road crossing experiments. Please welcome him with big applause.
Hello, 안녕하세요. My name is Ryan Kim. I'm currently a PhD candidate at NYU Tandon School of Computer Science and Engineering. So, first presenter, I want to thank everybody for coming to this series of presentations, and I hope we can all get along. So let me share my screen so that I can have this ready. Do you guys see my screen?
Yeah. Yep.
Okay. So my topic today is building verisimilitude in VR with high-fidelity local action models. So that's quite the mouthful. So I will try to explain a little bit the context of what our lab is interested in, and I hope we can go from there. So our lab, the SimSpace Laboratory at NYU CUSP, is really interested in this idea called geosimulation. It's this idea of building virtual testbeds to explore geographic phenomena. So what this entails me is that we bring in some well-known existing models that are meant to replicate behaviors in urban settings, for example, traffic flow models or a pedestrian crowd control and flow models. We bring them all together into this one virtual testbed, and we just sort of modify them a little bit to see how they interact with one another. And we explore sort of the nuances of how their interactions are going, and we can use that data to explore like actual phenomena that are occurring in the real world. So this is following this well-known concept called virtual geographic environments. So we take all these well-known models and we combine them into this one testbed that we can sort of explore all of these phenomena occurring all at the same time and in real time. So for a long time, my lab has been interested in seeing if we could use modern hardware to explore these phenomena, not from like a bird's eye perspective that a lot of these earlier geosimulation models have done, but see them from a very individual hyperlocal interaction between entities. So that will mean like pedestrian to pedestrian, pedestrian to vehicle, and sort of seeing if we can explore those from a very like in-depth perspective. And for a while, this was not really possible, at least when geosimulation first came out, because of the lack of hardware and data. But thanks to a lot of modern technologies, we have new sensors and new perceptions, edge computing and machine perception bring in so much data about the geographic environments in the real world. We can now use that data. And also, for me personally, I'm very interested in extending the geosimulation area into virtual reality, or augmented and virtual reality to be more general. So I don't know if we can do this. I like to ask the crowd, has anybody here actually experienced like wearing a virtual headset and like interacting with a VR headset before? Okay, so I get to talk about this a little bit. So the idea of virtual reality is we are essentially overriding your senses and tricking your senses into believing that something that is virtually there is actually really in front of you. That's the very standard definition of virtual reality. So in the context of geosimulation, what that means is that we can bring people into these VGEs and sort of see how they interact with these well-known existing models and seeing the nuances of that interaction. And this is very much beneficial for us in the sense that because it's a virtual environment, we get to modify these environments however we really kind of need them to be. And because it's all done in the safety of a laboratory, we get to gather so much data about their head pose position, their body orientation, their motion capture, their eye tracking, so many nuances to the kind of data we can collect that's honestly kind of hard to get in the real world from observation studies. So there's a lot of benefit going into using VR for geosimulation. My lab likes to term this immersive geosimulation environments. We embody people into these virtual simulations, and we sort of see if we can drive those hyperlocal actions I mentioned before into fruition between the humans and the virtual entities. That kind of brings up this natural question of what happens if we actually try to do that? Can we combine these VGEs and VR headsets to evoke enough believability so that people will bring over and translate their real world behaviors into the virtual simulation? We say this in the context that when it comes to VR, there's a lot of perceptions that it's more like a video game. It's kind of like an entertainment system. So we need to really understand how VR evokes real world behaviors and if it is actually possible. So what we did is what I first focused on was actually trying to do that. We built up a very virtual testbed for a very typical road crossing scenario. We have these well-known existing models for traffic flow. For example, we have the intelligent driver model to replicate the traffic flow. We have nav mesh from Unity, which is a combination of a reverse reciprocal velocity obstacles for obstacle avoidance and A-star for pathfinding. We bring them all into Unity 3D, which is our game engine that we've run the simulation on. And we just wanted to see what would happen if we threw people into that simulation. So this is quite complex because when it comes to these kind of well-known models, we need to modify them to interact with one another. This is a bit different from this general term called microsimulation, where microsimulations, we kind of bring them together into this one environment, but they don't interact with one another. So geosimulation is a bit different. We want to have them interact with one another, but that means we need to modify them a little bit to make that so. So what we did is that we induced a bit of unpredictability into the intelligent driver model by giving each vehicle a unique profile. We randomized some parameters about their vehicles, such as the distance between them and their header vehicle, their velocity, their acceleration, and we gave this sense of unpredictability to replicate that kind of behavior in the real world. We did the same thing with the pedestrians as well. So normally these will follow some very set paths and pathfinding. We enable them to be a bit unpredictable by giving them their profiles as well. And in doing so, we give the vehicles and the agents some kind of sense of having a state that controls their movement, their animations, and everything like that. For example, the pedestrians follow a kind of behavioral tree that allows them to transition between those patterns, those states, and it gives them this sense of state-based. It replicates state-based modeling. So there's actually some pedestrians who act more risky. They'll cross the road when they get the chance to versus those who don't. So we kind of combined these well-known models together. We threw people into the VR headset, and we just wanted to see what kind of data we could collect. We threw in, for our initial exploratory batch, we had 24 people come in. Ultimately, 20 people's data were used in our analysis. If I have time, I'll explain to them why those 4 were omitted, but 20 participants' data were collected, and we collected some subjective data and some empirical data. Subjective in the sense of we asked them some questionnaires for their presence, realism, and task load, which generally means difficulty of handling the simulation, and some empirical metrics, such as how many times did they perform red light violations, how many times did they get hit by the vehicles, and seeing if there's some pattern that emerges. So for example, we had this one participant who was trying to cross a road and he sees that there's a virtual pedestrian crossing. So he thinks it's fine to cross and he gets hit. There were some instances like this. So we also want to see why this was happening and see if there's some patterns that are forming. So this is quite a lot of data. I'll speed through this real quick. This is the presence questionnaire. We asked them, how did they feel being in the virtual world? And we got some very positive responses, positive being generally on the right, and negative being on the left. We got some really good data saying that they were captivated. They thought that the virtual world was believable. So this is good data because it's kind of validation for this IGE concept. They felt that the virtual experiments was very similar enough to the real world as well. Again, this is a good validation for this idea. when it came to the realism, they actually felt convinced to actually avoid the vehicles and the pedestrians, despite the fact that we didn't really encode any serious consequence to the simulation. So that already told us that by adding this kind of unpredictability setup into this situation, we could actually compel people to behave as they would and treat them as actual entities, not just some video game characters. When it came to task load, real quick, nobody really experienced any difficulties. There's no people that experienced motion sickness. We call it simulation sickness in the actual terminology. So again, this is also good data to show that VR headsets are compatible with these kind of systems. A lot of data, again, this is kind of speaking to the amount of the copious amount of data we could collect. I'll just briefly touch someone's highlights. For example, we can see that males performed a bit more riskily than females. They got hit more often by vehicles and perform more red light violations. This follows the well-known literature about like females tending to be a bit more cautious when it came to the road. We can also see some interesting trends where among the people of the age groups of our population, the younger generation generally tended to be a bit more risk-taking. So that speaks to maybe some concepts about urban design we ought to consider. We have some additional data such as trial duration. I'd be more than happy to go into this in more detail in a future discussion. So because we are interested in this concept, we also tracked their head orientation as idea for fixation, seeing if there's also some patterns we can gather from that. And we can actually see that people tend to pay attention a lot to the back of the head, back of the neck, back of the head, torso as kind of interesting areas of attention. This kind of follows literature that if you're following somebody on the road, you tend to pay attention to these areas because it gives you an idea of what to anticipate when you reach that position in the future. So this is good validation with well-known data as well. We can also see some interesting trends where for some reason people are paying attention more to the car signals than the walking signals. Again, this is something that we can think is worth exploring, and it kind of speaks to IGEs as a concept. So ultimately, I want to end off by saying what happens when VR happens. Users were sufficiently convinced that this was real enough that they could employ their real-world collision avoidance behaviors. There's some new interesting results that came from it. And this is sort of like we can use this testbed to explore new concepts. I don't know if we have how much time we have left to discuss some caveats for VR. Again, I'd be more than happy to discuss these in the future. But overall, this is a good starting point for some research projects that we have. So thank you. I don't know if we can do QA, but thank you for listening.
Thank you, Rayan Kim, for the very excellent presentation. We will have about time to have about 2 or 3 questions. For the first question, we have could you further elaborate the implications of your research in terms of urban planning or policy, or how your research can benefit the real-world cities?
Excellent question. So what this means for IGEs and in relation to the real world, what this means is that if because of when we kind of look out the window, we can see that there's a lot of new changes that are happening. For example, we have new autonomous vehicles that are starting to populate the road. We have new modes of transportation, such as electronic scooters and bicycles. And a lot of cities, at least big metropolitan areas, that tend to be built upon known knowledge based on early research. But with these new advent of these new technologies, I think it's a good thing that we can start questioning some of these implications and this well-known knowledge, and maybe reassess some qualities about the urban way that we are designing urban cities. So these IGEs and using VR to see how people are reacting to these virtual environments is kind of a good way to safely test different urban street designs, see how they're interacting with, for example, autonomous vehicles. There's some literature that has tried to do that already. And so this is kind of like a good starting point to maybe get more data about how people are reacting to some of these areas of attention in the streets and seeing what kind of patterns form. I hope that answered your question.
Great. Thank you. Yep, there is one more question. It is, the study included 20 subjects. And have you considered including diverse group of pedestrians, such as seniors and disabled persons?
Yes, so that's what I was talking about when it came to the extension of the project. Our initial test group explored 20 participants who were within the age range of like 19 to 32-ish. I think it will be a good way to extend it project will be to include that bigger diverse group of people. One thing that that is well known in the literature is that age and demographic, and also where you grew up, not just demographic, but where you grew up also has an influence on how you are interpreting the road behaviors of vehicles. And so what we can do is that, for example, when it comes to elderly people, we realize that their motion, their ability to react to certain things is much slower than their processing time. They can realize when a car is going to hit them, for example, but maybe they might not be able to react fastly, or maybe by the time they get to the road to cross, things have changed so much that they have to reassess. So yes, I think a natural extension of this study would be to bring in some more diverse in terms of age group, country of origin, maybe nationality would be a good indicator, and sort of seeing if there's also these patterns exist or if there's some nuance to it.
Yeah, thank you for your excellent Q&A, but we have one more question actually, but we are running out of time, so maybe you can let them know of your like, you can talk through the chat box of Zoom, or yeah, yes. And for the next speaker, we'll have Bingqing Liu from NYU. She's a PhD candidate at Tyndall Engineering School, and her presentation title for today is On-Demand Mobility as a Service Platform, Assignment Game with Guaranteed Stable Outcomes. Please welcome her with the round of applause.
Can you guys see my screen right now?
Yeah. Yep.
So, okay, I'm gonna get started. So, hi everyone, this is Bingqing Liu from New York University, and I'm here to present a mobility as a service platform assignment game with guaranteeing stable outcomes. And this work is advised by my supervisor, Professor Joseph Chow. Okay. So first, let's look into what is mobility as a service. So basically, mobility as a service is a type of platform that incorporates different types of mobility, like different type of mobility services. For example, Uber, Lyft, and traditional mass transit will be all taken into this platform. So users on this platform will be able to book a series of services, like a trip chain, using like this joint digital channel, like using one payment. Okay. So there are already like a lot of examples that are already deployed around the world in major cities. So this kind of mobile service platforms, because it involves like different players altogether, like different mobility providers providing different types of services with different operation policies. So its modeling becomes more challenging. Okay. So let's look at what are decisions being made in this type of platforms. First of all, it involves the platform itself. It can be able to decide on like some restrictions on the services. For example, what service regions, like there can be like fare bundles, there can be like subsidies, taxes, like that. And then we have the mobility operators, the service providers. They can decide on where they want to provide the services and how much service they want to provide, like the line capacity or the fleet size, the routes where they want to operate, and the service regions they want to cover. And we have the users. They're going to choose their path to connect their regions and destinations. Okay, so because we have these complicated operators, so if we look at the literature, there are a lot of like other existing methods that look at these markets that involves multiple operators, but most of them are looking at non-cooperative games. So they ignore the possible cooperation between these mobility providers. But under the environment of mobility as a service type of platform, these mobility providers are going to be able to cooperate with each other to benefit each other through their cooperation. And they don't typically look at the role of a platform or a regulator that would be able to push the platform equilibrium towards a certain direction, like towards a direction with higher efficiency or higher environmental benefits, like that. So except for that way of looking at these type of platforms, we can also look at it as an assignment game. So that is kind of like looking at the relationship between the operators and the users, not just looking at the relationships between operators and then use that relationship to form an environment within which the users make their choices. Like with assignment games, we're going to be able to directly look at the interaction between the users and the operators. So assignment game basically is modeling a set of stable matching between a set of buyers and a set of sellers. So in our case, our sellers are the mobility providers, which gives the services, and our buyers are the users. And the platform come into play with their policies, subsidies that can be restrictive or pushing the matchings towards a certain direction. Okay, so within mobility as a service platform, we have this kind of many-to-many assignment game. Why this is many-to-many? Because the users are choosing paths, and each user, their path is going to be multimodal, and it's going to be operated by a set of different operators. And one operator is going to be serving like a bunch of users. So that is why this is a many-to-many assignment game. So this paper already looks at like the fixed route service within this subnetwork, but ignores like other different operation strategies, like on-demand operation strategies. Okay. And if we consider the mobility on-demand services, we'll see that the decisions that the operators are making is very different. So for the fixed route services, they decide on the routes, and they decide on the line capacity or the service frequency that decides the capacity. But for the mobility on-demand services, they decide on the regions they're going to cover and the fleet size that they want to deploy in their service regions they want to cover. So this paper, it looks at both these types of services, but it ignores the multimodal side of this type of like combination, and it lacks a spatial component. So while our study is looking at, first, we incorporate both the fixed route transit and the mobility on-demand type of services. And we have a mechanism agnostic cost allocation with stability guaranteeing, and we consider a full OD demand table. Okay, so in order to model the fixed route services, there are two decisions that these operators are making. First, the routes, like which part of the line I want to provide service and which part of the line I may not want to provide my service. And the second is what frequency I want to provide, which decides on the capacity. So to be able to model this type of decisions, first, we are using a binary variable to represent if a segment of line is chosen to be provided with services. And we use parallel links to represent different service choices, like frequency choices. So that is for the fixed route services. And for the mobility on-demand services, the choices they have involves the service zone, like which zone I want to cover, and this fleet size decision, like which part of the region that I want to, what's the fleet size that I want to deploy within the service region that I want to cover. So for example, if one mobility on-demand provider is choosing between these 4 zones, if all of the 4 zones are being covered, they're going to be service between each pair between these 4 zones. That composes a full, like a complete graph connecting all these 4 zones. And then we use different complete networks that connect these 4 zones to represent different fleet size options. And then each node within these complete graphs is going to represent a combination of whether a zone is covered and what fleet size is going to be provided here, that combination of the decisions. Okay, so then these subgraphs are going to be connected with the walking and transit network with access links. And the cost of those access links is representing the wait times. And the wait times are the function of the flow on the link and the fleet size deployed within that region. So we also provide an option for the users to opt out of our system. So by connecting each OD pair with a dummy link with a pre-estimated average cost of the outside options. Okay, so then the formulation is like this. So we take the network setting as an input to extended multi-commodity network design problem, which is the MCND, and it outputs all the decisions that we just talked about. And the objective is a Beckman's form of the trouble cost on the user side plus the operation cost of all the different types of operators. And with the constraints, we consider the choices of the capacity, the choices of the MOD nodes, fleet size, as well as the node conservation, which represents the OD demand. Okay, so this is giving us a nonlinear mixed integer problem, which is going to be hard. So then after having the matchings, we decide how the utility is going to be split between the users and the operators by doing the pricing. So in this pricing problem, we have the decision variables include the user's payoff and the fare of the services, which represents the payoff that the operators get from there. So basically the mechanism is like this. So by making one trip, this user is generating a trip utility, like a welfare for this society to share. And that total payoff is gonna be, so basically, but making this trip is gonna cost us some money. That is gonna be like the trip cost plus the operation cost that make this trip happen. Basically, the cost of making this trip happen on both sides of the users and the operators. And then what is within between these two values is the total payoff that can be shared by the users and the operators. Okay, so then after setting the fare, the operators decide what amount I want to take from here, and the rest is going to be the user's payoff. So that's how we decide on the pricing. And by having the stability conditions and making sure the operators don't lose money, we're going to have like a set of conditions that decides on this the fare that we're going to be able to set. So we can solve for the buyer's optimal, maximizing the user's payoff, or the seller's optimal, maximizing the seller's payoff. Okay, so yeah, I'm gonna skip this time-wise. So for the solution algorithm, as I mentioned, the problem is NP hard. So we're designing this solution algorithm to solve it. First of all, because it is a mixed integer program, we relax the integer constraints using a branch and bound framework. And then it becomes a capacity constraint traffic assignment problem. And then we relax the capacity constraints with Lagrangian relaxation, and we use subgradient optimization to solve for the Lagrange multipliers. And then after that, converge, we assign the flows to the paths, and this concludes this branch. Okay, so that's basically the mechanism of the solution algorithm. So let's look at some numerical cases. So first, we look at this extended two-fault network with these assumed with 30 OD pairs and these assumed access link costs. So for the base case, we see that there is no operation of these mobility on-demand service providers. So this means that mobility on-demand setting is kind of expensive in this case. But when we look at a heterogeneous case, so this heterogeneous case means that we have a higher income group and a lower income group, but the total income of the society remains the same. In this case, we see that there are some operations for the mobility on demand, but that part of the service is only serving the higher income group. And the lower income group ended up mostly unserved, so they're leaving our platforms. So this kind of reflects a potential equity issue among like different income groups. So then we try to subsidize one of the operators in here, but we see that the assignment remains as the same as the base case. So this subsidized operator is still not operating. So the reason is basically that even if it has a lower, this assignment with its operating has a lower system total cost. but it is not stable. So the users on this red path has some incentive to switch to another cost. So that is to another path. So that is basically controlled by the cost allocation problem. So yeah. So to summarize, we propose a mobility as a mobile service platform design method considering both fixed route, transit, and mobility on-demand services. And it is formulated as a nonlinear mixed integer programming. We propose an exact solution algorithm for it, and that method can be applied to the design of mobility as service ecosystem, or it can be applied even to a general multimodal transportation service kind of like environment. Okay, that's my presentation. Thank you. Ready to take any question.
Thank you very much for the presentation. And maybe we'll have time for one or two questions. First one is, can your model accommodate new modes of transportation to Cuba's urban air mobility? And on top of that, if so, then would it be possible to assess the feasibility or serviceability of other modes of transportation in multiple scenarios?
Yes, I think so. Yeah, as long as it is able to be modeled as for example, I think when we're modeling urban air mobility, its operation strategy is going to be very similar to mobility on-demand services, right? It's going to be covering a maybe less flexible, less on-demand. There will be a station, a point is going to be covering, there's going to be I assume frequency or something like that. When there's more users using it, we can set a weight function that incorporates that can be a function of the amount of users at this time, at this point, and the amount of aircraft that we have in this area. So I think the model can be able to use to cover urban air mobility type of service. Yes.
Thank you. And we'll have to jump off to the next presentation due to the time limit, and you can discuss within the chat box for the next question. Thank you.
Thank you.
And for the next speaker, we'll have Rayan Succar from NYU. His presentation on Fame for Surprise, how fame-seeking mass shooters diversify their outings. Please welcome.
Hello, everybody. Can you hear me?
Yeah, perfect.
So I'm Rayan. I'm a PhD candidate in the Department of Mechanical and Aerospace Engineering, affiliated with the Center of Urban Science and Progress. I'm a member of the Dynamical Systems Lab here at NYU. Thank you for having me tonight. And what I'll be talking about is a little bit different of what we have seen. I'll be talking about hypothesis-driven work to understand a specific case of mass shooters. First of all, if you're not very familiar with the topic, mass shootings is an incident where somebody goes on a rampage, killing people publicly. It's a problem all around the globe, but it's predominantly in the United States. Actually, yesterday there was a very bad incident in Maine. And there are different motivations on why these mass shootings happen. For example, relationship problems, employment issues, the use of psychosis. And one interesting motivation is seeking infamy or fame seeking. And although it's the least frequent, it's the most lethal. So understanding the behavior of those fame seekers is crucial. It's crucial to help with this problem. So what are fame seekers specifically? Fame seekers are people who executed their attacks in the sole purpose of gaining infamy. And the way to identify those perpetrators is through things that they have said, things that they have done. For example, this first fame-seeking perpetrator said to the police after being apprehended, I want to get known, to get myself a name. And there are other means to identify them. For example, some of them will streamline their attack. They will post videos, they will send material to newspapers so they can get known. Now, in order to understand the behavior of fame seekers, we first need to understand fame. And fame has been previously studied well in the literature, and it has been always associated with with success. For example, we all know the physicists who were successful in their field. And for chess players, the higher your rank is, the more famous you are. And this is also the case for fame seekers. First of all, they know that the more they kill, the more fame they attain. Because one of them, for example, said, the more people you kill, the more you're in the limelight. And this has been shown through a recent study by Silva and Capellan, where they showed that lethality is a significant predictor of the media coverage of mass shooters. So the more they kill, the more the media will talk about them. However, we want to propose an alternative, or maybe not an alternative, but another perspective of this phenomena, which is surprise. Surprise has been known to have different effects on a human. For example, here you can see an example of blood oxygenation level dependent signal using fMRI and the lateral prefrontal cortex. And in this plot, you can see the gradient on the background shows the places where we expect a peak in the activity. And the green region is for the encoding of the signal. The yellow region is the rehearsal of the signal, and the purple is the recognition. And we see two interesting things here. Novel signals have higher peaks, and they have higher delays. It means that they leave an impact on us, and we need more time to process them. And our objective from the study is to link surprise to those fame seekers. So the first thing we did was start by collecting data. We collected data on 189 mass shootings from 1966 to 2021 from three sources, basically, mainly Mother Jones, the Washington Post, and the Violence Project. And for each mass shootings, we focused on two main features, among others. But the two main are the target group and the shooting location. The target group described the category of the group that was targeted from this attack. It could be students, it could be religious groups, it could be acquaintances. The shooting location also describes where the shooting happened. Did it happen in a school? Did it happen in a religious place? Did it happen in a restaurant? Etc. After having this descriptive data set, we needed a way to quantify surprise. And the way we did that is we relied on the information theory. Specifically, we defined surprisal the way Shannon did. And so the way he did it is that surprise of an event is simply the negative logarithmic of the probability of that event happening. The lower probability the event would likely to happen, the higher the surprise it's associated with. And with an illustrative example, let's consider the first incidents characterized by a black color. We see the next two ones are also black. Since they are black, according to the history, they are not very surprising. Suddenly, we see a red incident, which is very surprising because it never appeared before. However, if we keep going with red, it's not very surprising anymore because according to the history, it's been frequent. However, here, if we see a black one again, it's more surprising than the last time we saw it because according to the history, it's not that frequent anymore. And so on and so forth. Here, for example, if we see something new, it's very high, it has the highest surprise. Now, after having this framework for quantifying surprise, we quantified the surprisal for each of the shootings that we have in our dataset for the two features, target group and shooting location. And we see very strong statistical difference between the surprisal of fame seekers and non-fame seekers. Specifically, A fame-seeking mass shooter is 3 times more likely to have executed a more surprising attack than a non-fame-seeking mass shooter, which means that those fame seekers are actually trying to have a novel attack, an attack that never appeared before. Now, the natural next question that we could ask is, does this, what they are doing is actually working for them? Are they gaining more fame? And in order to do that, we need a robust measure of fame. And after long research, we found out that this is one of the best measures we can get, which is the Wikipedia traffic data. Here you can see a time series. Each point represents the number of daily visits a Wikipedia page has been accessed. And I'm showing here the most famous 3 mass shootings along the years. This is why this is a good measure of fame, because of 2 things. First, it is a collective measure. It's not a media coverage where it could be biased from one media source. It's a collective measure from the people who are going to these Wikipedia pages. And secondly, it is stationary over time, meaning it will improve our statistical studies because we could have extrapolations on what fame would have looked like in different times. So after having this robust measure of fame, we simply investigated the correlations between surprisal and fame. And from these 2 scatter plots, we see that surprisal is correlated with fame, which was measured through Wikipedia. These dots represent mass shootings. The blue one are fame seekers, the orange one are non-fame seekers, and the shaded area represent the covariance. And we see that it's significant as it's tilted, with approximately rho is equal to 0.4 for the 2 cases. In summary, we discovered 2 main claims of this work. First of all, fame seekers carry attacks that are surprising with respect to their predecessors. They are different in their attacks. Second, the more surprising an attack is, the more fame it attains. And what are some possible implications of that? We propose that the media should be a little bit vague when reporting these incidents, because the more ambiguous the media content, the less information fame seekers have at their disposal to plan their next attack. And how would that be possible? For example, here, instead of saying massacre shatters Brooklyn school, we can say shooting in Brooklyn and not specifically mention school. So fame seekers won't try to differentiate from them. Now, we're not making this as a very bold claim. It's just simply that we're opening the door for research to focus on how they should report these incidents to minimize the damage of these mass shootings. Thank you for listening. If you are interested, you can read. This is an already published work, and I'll leave the room for any questions.
Thank you, Rayan. We have several questions for you. The first one is, with your findings, can you possibly identify some, like, maybe in categories such as schools or like other parts, to like where are more exposed to such shooting events?
Yeah, so those shooting events are mostly in urban areas, and they are around like you rarely see shootings that happen in very rural places, because especially those seeking infamy, because they want to make a scene, they want to get they want something new, which is mostly predominantly in urban settings, and they also want to maximize their lethality. So it's also a perfect place for them. This is why it's important for urban science, basically.
Thank you. And the next question is, could you explain more why you think wiki page views as a meaningful measure of fame? Do you have any studies to support?
Yes, so I'll give you a comparison with other different measures of fame that has been previously been used. One of them is media coverage. With media coverage, it's a bit tricky because you'll have to go through the media, read the articles, manually see if they talk about this specific event or not. And it could be biased because previously in old years, they did not publish as much news article as of today. So it does not have this stationarity in time. It could also be biased from location. A shooting happening in New York won't be probably covered in the Los Angeles time, for example. For our case, it's stationary over time. We can make all the claims that we want. And it's a collective measure, meaning it's not from one source, it's from the people. It's how they proclaim fame to be. Another measure of fame that people used is Google hits, where basically you go to Google, you type the name of a person, and you see how many pages Google will return to you. But then again, now with the growing number of pages that talk about random stuff, you'll have what we call namesakes. Basically, if you search the name of a person, you'll have different persons with the same name talking about completely different things. So it's very noisy in a sense. Yeah, and also like our measure is pretty much noiseless because you either go to a Wikipedia page to read about the thing, which means it's more famous, or you stumble upon this page accident. But then again, if you stumble upon it, you read about it, it's also more famous. So it's pretty much noiseless.
Okay, thank you. We have the last question. Defining surprisal as the entropy of is fascinating. Do you think the study can be applied to other types of extreme social phenomena, such as suicide and increasing depression rate?
It definitely could. It's very simple. That's the beauty of it. And it could be applied to humans as well to animals. We can possibly look at how leadership in animals emerges from surprising events. You can see how we all know that leaders in all settings are unique people. Unique people meaning that they done things that were surprising, basically.
Okay, thank you very much. Thank you all from NYU for joining this late in the evening. And for the next speaker, we'll have the first KAIST speaker, Dr. Namwoo Kim. He will present his research about learning representation of communities, social vulnerability from human mobility. Please welcome him.
Can you hear me? Okay. Good morning, everyone. I'm Namwoo Kim, a postdoctoral fellow working on urban analytics. And the topic of my presentation today is learning representation of social vulnerability of communities from mobility data. And this research was conducted as a collaborative effort between myself, Professor Takayori Abe, Professor Chanyoung Park, and Professor Yunjin Yoon. Recently, significant economic and human losses resulting from extreme weather or disease outbreaks underscore the importance of understanding and assessing the social vulnerability of communities. Social vulnerability refers to the susceptibility of individuals or communities to the adverse impact or natural hazard. These days, major initiatives like United Nations or Center for Disease and Control in US underscore that identifying vulnerable location and quantifying the vulnerability are crucial for disaster planning and mitigation purposes. However, the reliance on extensive surveys or fieldwork in current methods for assessing social vulnerability poses challenges in delivering timely informed decision-making. In detail, to identify socially vulnerable communities, many existing studies have assessed social vulnerability by integrating various census variables, such as age, gender, housing, socioeconomic status into composite indexes. However, collecting census variables typically involves time and cost-consuming process, such as decennial census survey to gather information on demographics, socioeconomic status, and household characteristics. As shown in this table, several efforts have been made to actively explore location intelligence-based approaches to infer socioeconomic and demographic status through the lens of human mobility. Considering the successful extrapolation of regional socioeconomic and demographic details from human mobility data, utilizing mobility data can facilitate the capture of social vulnerability signature in communities. So here is the research goal and objectives. The main goal is to capture social vulnerability signatures in communities from mobility data. Specifically, we incorporated the temporal dynamics of human mobility for capturing social vulnerability signatures using time series contrastive learning. And the proposed model is evaluated on 3 US cities, Chicago, New York, and Washington, D.C. This is the overall framework of the proposed model. We first pre-process region-wise hourly inbound and outbound trips. Subsequently, a two-step data augmentation process is applied to the provided mobility time series data, and 3 encoders were utilized. This FI, FIO, and FO. And those are fed with the augmented data. Here, FI and FO run inbound and outbound specific human mobility patterns in each region, while FIO extracts semantics containing both inbound and outbound specific features. Then the projection headers G are applied to each of the encoders to apply the contrast alerts. And then we obtain the embeddings from the proposed model, which is MobClear. And then the embeddings were used to predict the social vulnerability of the communities. For the data set, we used only 2 weeks of taxi trim records or ride-hailing trips to generate influx and outflux time series data. All the data sets were sourced from the open data portal of the each cities. And we used social vulnerability index from Center for Disease and Control as the ground truth of social vulnerability of the communities. And then we compared the proposed model with the following 7 baseline methods, including low features, graph neural networks, and the state-of-the-art models of the time series contrastive learning model. And for evaluation, we trained a simple linear regression model at the top of the network. And we used the R-square and Spearman correlation metric to evaluate the prediction performance of our model. And please note that once pre-training is completed, we solely use the FIO encoders for the downstream applications. And here is the prediction results. The experimental results show that the proposed model, our model, outperformed baseline models by a large margin. And further, we conducted experiments varying the source target city pairs and evaluated the social vulnerability prediction performance. In this figure, please note that the higher R-square results are highlighted in bigger green circle. The diagonal line in the figure describes the scenarios where the source and target is the same, indicating a non-transfer setting. The results demonstrate that our method outperforms state-of-the-art models across all 3 cities. And moreover, every transfer experiment achieved better performance than the best baseline. For example, in the Chicago to DC and New York to DC transfer learning scenarios, our model achieved an R-square of 0.415 and 0.439 respectively. However, the best baseline achieved an R-square of 0.371 in the non-transfer setting. The outcomes of the transferability test indicated that the approach can be employed in areas where social vulnerability has not been evaluated. So let me give you the conclusion. In this study, we propose time-treat contrastive learning model to predict social vulnerability of communities. Traditionally, social vulnerability assessments are reliant on data from laborious and expensive sensor surveys. However, the proposed approach achieved accurate predictions of social vulnerability using just 2 weeks of mobility data. In addition, the results of the transferability test indicate that our approach can offer valuable insights into proactive responses to future threats and disasters in areas where social vulnerability assessments have not been conducted. In our future work, we plan to enhance our modeling by incorporating additional information such as point of interest and street view images. This inclusion is aimed at further improving the results, the overall performance of the proposed approach. And thank you for listening.
Thank you, Dr. Nam Kim, for the great presentation. And we have several questions coming up. The first one is, are there any measurements similar to SVI in other countries? And would this framework be able to transfer to cities outside of the US?
First of all, the Center for Disease Control published the social vulnerability index of all the US cities. But outside of US, we can hard to find the index of the social vulnerability, so we use the social vulnerability index from the CDC.
Okay, then for the other question, is there any reasons for choosing 3 cities of Chicago, DC, and New York? Why not differentiating the size of cities, such as since the cities have all similar sizes?
In this study, we use the mobility data. The taxi trips or the ride-hailing trips. So actually, as far as I know, there are only 3 cities that publish the trip data in US. That is Chicago, New York, and Washington, DC. So I use the data set of the mobility data in those 3 cities.
Thank you very much. And we have the other KAIST presentation from KAIST by Dr. Wonjung Kim and Dr. Seoungchul Lee. They will present about socially aware control of devices in urban space. Please welcome them with big applause.
Okay, hello. Okay, let's start. Hello everyone. We are Wonjung and Seoungchul from School of Computing, KAIST. And we are very happy to present our research, socially aware control of devices in urban spaces. And let's start with an example. So have you ever ridden a long distance bus overnight? Let's say 8 hours. Imagine you feel the air conditioning in a bus is too cold. And you also guess that other passengers feel the same. Or let's say you are a parent and you bring your child and the AC is too strong. And this time your child sniffles for 8 hours, but you cannot do anything. The AC is actually supposed to give comfort to passengers, right? But it gives discomfort instead. So what brings this irony? First, it's usually the case that the passengers have no control of the AC. Second, maybe you are lucky enough to find the control panel of the AC, but you notice that other passengers may not want to increase the temperature. And you will find it hard to ask other passengers or the bus driver if they will agree or not. So you end up doing nothing and endure the situation. Such an irony happens not only in the bus, but again and again in our daily lives, like riding in a tourist bus, loud rock music in a pub, and a TV in a cafeteria. In many public spaces, the spaces are shared, but not the devices in the spaces. Are they really public? The three key factors make them not public. 1, absence of control. 2, exclusiveness of control. And third, the social hurdle of control. The irony happens not just for the case of AC in a bus. The same irony happens for lighting fixture, humidifier, public display, and speaker, and so on. So the opinions of many people are often just ignored. Currently, the person who holds the control interface decides everything. So our vision is the direct democracy for public IoT. So here you can see the picture of a subway. Each passenger expresses his own preferred temperature, and these preferences are gathered and reached to a consensus. And the consensus is instantly reflected to the AC. So we name this as a social control and use. However, the social control and use has many challenges. First, diversity and heterogeneity in users, devices, and spaces. Users have different preferences, and devices are made by different vendors, and also spaces have different social rules. The three entities are already complex, and further, the interactions among the three entities make the problem even more complex and dynamic. And second, these problems are further complicated by the uncertainties in public spaces. We don't know when the visitors come and leave, and we also don't know if they will know each other or they are strangers to each other. So to this end, we built HiveMind, a new system for social control and use. It transforms an exclusively controlled device to a public device. So we use IoT's capability to interconnect participant devices and spaces. In a high level, HiveMind collects the visitor's preferences and mediates them to derive a consensus and reflects the consensus to the devices. Social control and use is a very complex problem. The system should mediate dynamic interactions among devices, spaces, and participants. The system should address diverse sets of technical issues, and let me name a few: authorization or control interface design, aggregation policy, device interoperability. So how can we manage this complexity of the unexplored problem? As an initial attempt, we suggest 5-layered architecture. We applied the principle of separation of concerns, and we grouped the problems into we grouped the technical issues to drive these 5 layers. So device connectivity layer, participants discovery and authorization layer, social control interaction layer, aggregation and consensus layer, and device control layer. And our HiveMind system is organized following the 5-layered architecture, and we'll skip the details here. And we also made a mobile app for HiveMind, and these are the example screenshots of the app. And we deployed HiveMind to many real-world public spaces: cafeteria, pub, food court, lounge, and office, and also the auditorium in the KAIST. We installed 6 types of actual devices: TV, speaker, heater, diffuser, mood light, and microphone. And we deployed HiveMind for a month and also conducted survey and interview with the visitors. Okay. Let me continue our presentation. So I will introduce our second case, Social Appropriateness Guardian, or SAG in short. So this piece of work is about helping people be more considerate about noise issues. So again, let us give you an example. So I believe you haven't experienced that envelope noise from a vacuum or mixing machine disturbed your sleep or, say, meditation. And in such a situation, you may have complained that, why now, this early in the morning? But let me ask a different question. So, have you ever turned on a vacuum to intentionally disturb your neighbors? Probably not, I think. So I think it's interesting because there is no offender, but only victims. So our research vision: what if we could see the discomfort of neighbors? So as shown in the picture, when you are about to make a coffee, what if your coffee maker advises you that the coffee maker's noise will disturb the meeting of your colleagues? So it will make it easier for these office members to be considerate to each others. Or conversely, if the coffee maker tells you that there will be no discomfort predicted, you may use it without worrying noise nuisance. So to this end, we built SAG. So SAG is a situation-aware noise discomfort advisor system. SAG transforms these appliances around us, which are ignorant to neighbors' discomforts, into considerate ones. In high level, SAG collects occupant context in the vicinity of appliance and predict potential discomfort of neighbors and suggest also resolving actions. And using this information, a noise-making appliance can guide the user to a considerate action. So we prototyped this SAG system and deployed this system to 3 real-world high-density spaces, 3 offices and 1 go시원. go시원 is highly packed residential accommodation common in Korea. The right picture shows the go시원 we deployed the system, and so we deployed SAG for 2 weeks and interviewed our participants after that. Okay, let me conclude our presentation. So we introduced a new problem of socially aware control of devices in urban spaces. We propose first-of-kind systems for socially aware control of devices. 1, HiveMind, and 2, SAG. We deployed these systems to many real-world urban spaces, including cafeteria, pub, auditorium, and go시원 for many weeks. So that's it for today, and thank you.
Thank you for a very fascinating presentation. I have actually one question. So since you have deployed these sensors to the devices to the real world environments, do you have any feedbacks or data collected from those deployments and analysis of the results?
Yes, of course. As we thought, in both studies, we deployed the system to the real world, and we got the surveys and interviews from the visitors. So, of course, as you may know, just the result is positive. So many people, and most of the people, like that they can control the devices in public spaces, and also that control of the devices can be decided by the public people. So sometimes that even the device state is different from their own preferences, they could accept the result because many of the people like the current state of the device. And similarly, in the SAG project, people are also like that. They were not aware of the neighbors, the state, for example, in whether they are in sleep or not. So they actually had a problem in using the hairdryer in the morning. So they were concerned on making the neighbors wake up. But with the system, they could avoid such an embarrassing situation. So they felt they are comfortable and they could be a more considerate to the neighbors.
Okay. Yeah. Thank you very much. I have no one. Yeah, I'm pretty much sure that everyone liked it about the device. Thank you for the presentation, and we finally have the last presenter from NYU. Actually, from NYU AD, but unfortunately, the time for the Abu Dhabi is 6 a.m. right now, so we'll instead have a recorded video for the presentation of Dr. Ilia Papakonstantinou. Can you see my screen? Yeah, please welcome her. Please welcome Dr. Ilia Papakonstantinou.
Hello, everyone. My name is Ilia Papakonstantinou, and I'm a postdoc working with the research group of Professor Samer Madanat at New York University, Abu Dhabi. First of all, thank you very much for the invitation to give this presentation today, and I apologize for not being able to be present real time due to the time difference. So I welcome any comments or questions you may have via email. I have added my email at the last slide of my presentation. So let's go ahead and start. I'm going to share my screen. Today I'm going to talk about our recent work on coastal protection strategies to minimize traffic disruption from inundation due to sea level rise, specifically for the case of Abu Dhabi. Sea level has been rising with no doubt, and for the past decades, many scientists are focusing on the prediction of the future sea levels. Some are more pessimistic, some more optimistic, but overall there is a very clear increasing trend. This sea level rise interacts with coastal infrastructure and may lead to the disturbance of operation or even permanent damage of vital parts such as hospitals, schools, airports, etc. The cost of such damages is very high. Just to mention an example, the 1996 flood in Boston costed $70 million USD in property damage. Now, what is more interesting and relevant to our work is the interaction of sea level rise with the transportation network. Links are disrupted, and some may be of great importance, such as bridges or tunnels that have no easy alternatives. There may be capacity reduction, such as lane closure, or accessibility reduction, such as subway station closure. All these may lead to significant delays in the network. These impacts are not local. They may be amplified further inland and not remain at the coastal areas due to the rerouting or queue spillbacks. Our approach is to use results from the hydrodynamics modeling and see how our transportation network will adapt to this possible rise of the seas. For the adapted network, we see how the traffic will be rerouted, aiming to measure congestion. In this specific case study, we focus on the area of Abu Dhabi, which is the capital of the UAE, and our university is located here. This is a country with very low elevation in general, and it has a lot of natural islands, so it's very vulnerable to sea level rise. We consider partition of the shoreline that is informed by the pressings along the coast of the in the urban structure framework of the Abu Dhabi plan. In this work, we consider that each pressing can be either protected completely by installing a levee along the shoreline or not protected at all. For notation purposes, we consider that the case P01 denotes that only the first pressing number 1 is protected. So let's see the process of our methodology. First, we use the results of the hydrodynamic simulations as inputs to identify the inundated areas and specifically the inundated links. Then removing those links, we end up with reduced networks for which we do a new traffic assignment. We explore several cases, starting from the marginal cases, so what happens when only one precinct is protected. And the aim is to identify combinations of precincts that, when protected, lead to the lower congestion levels possible. For the coastal hydrodynamics model, I will say a few words, but there is here the citation of this published work from Dr. Cho and Dr. Sun for more details. So the model consists of 3 separate models. The first is the Delft 3D model that deals with the tidal water levels. The second is the SWAN model that deals with the storm surge. And the third is the empirical model that deals with the wave run-ups. So the combined effects give the peak water level that we use. Using this water level, we overlay with the topography. This is our way to compare the peak water level with the elevation from the digital surface model that we have in 12 meters resolution. And in this way, we can identify which parts and specifically which links are flooded. Now, we select all those links as well as the links that are isolated because other links around them are inundated, and we remove them from the network. And we end up with a reduced network, which is used for a new traffic simulation. For the traffic assignments, we use the STEAM simulator, which is a regional strategic simulator that considers the transportation network in 2040. It has all the supply side because it's used by the Abu Dhabi government. And also it has all the changes in land use that are predicted to happen by then. This is a simulator that is not accessible to the public, and we had access to it due to our collaboration with the ITC of Abu Dhabi. Now let's focus on the metrics we use. The first subset refers to mobility. So we have the vehicle hours traveled, the vehicle kilometers traveled, and the VHT per vehicle. All these are network-wide values. We also use the volume to capacity ratio to show the congestion along streets. And then for accessibility, we look at the number of vehicles on the network that show, in fact, if commuters cannot realize their trip due to very high travel times. For comparison purposes, we use percentage changes instead of absolute values. Now let's move to the results. First, we look at the impacts in terms of the hydrodynamics. If protecting a precinct may affect the flooding in multiple other precincts. Let's see this matrix here. It shows the changes in inundated areas in different precincts. So we protect each individual precinct, and here the columns show the protected precinct. We can see that most protection strategies reduce the inundation within the protected precinct. In some precincts, the levees lead to the water to go to other parts of the shore, increasing flooding in other precincts. For example, this is the case for Musafa P1, P01. Protecting it increases the inundated area in P2. Yes. Sorry. We can see that there is a clear hydrodynamic effect of protecting individual precincts, but this is not the case for traffic. For the traffic network, we need to find combination of precincts. It's more effective than protecting just one or two specific parts of the shoreline. First, we see the case where no precinct is protected and the case where all precincts are protected. The green outlines show the levees around protected precinct boundaries. The black, the inundated links. The white, there is no congestion, so the VC ratio is smaller than 0.8. Pale red is greater than 0.8 and less than 0.95, and the very dark red is more than 0.95. For the P-all, so the case of full protection, all bridges that connect the main Abu Dhabi island to other islands remain operative, while at Penang there is only one bridge that is accessible. Sheikh Zayed bridge, this only one bridge remains open, but it's a major bottleneck. So the congestion levels will of course increase vastly. There is also accessibility reduction as links are flooded or isolated. This is why there is a smaller transportation network in figure A than in figure B. The number of vehicles also decreases by approximately 30% for the case of no protection. But despite all this, the total network VHT is higher by 20% for the case of no protection. And this is because of rerouting and congestion. So we have more VHT and less cars on the way. Obviously, the P-all is the best case scenario. It's also the most expensive. So Penang is the opposite, the least expensive but least effective. That's why we need to find a scenario that leads to satisfactory levels of accessibility and mobility, but with lower costs. Here is a schematic diagram of protection scenarios and the main traffic arteries that are protected, and we will explore some of those. Focusing on the case of protecting Yas and Saadiyat Islands, so P8 and P9, There is still accessibility for the island parts. Only one bridge connecting downtown to the mainland remains operative. We can see it's the red. So the vehicles from the eastern islands to the CBD reroute through this bridge, and obviously this creates a very big bottleneck. That's why we have a very high percentage of increase in VHD per vehicle. Now we are moving to the case of protecting only Musafa P1, the first precinct. Here the hydrodynamic model shows that water enters the precinct from the west, and the rest of the network is similar to the case of no protection. So the eastern region's connectivity and accessibility are heavily affected. We also observe higher travel times caused by hydrodynamics and not the network. So the percentage change of VHD per vehicle is worse than P9. Moving to the case where we protect P1, 2, and 3. So Musafa, Ben, El Jesrain, and Grand Mosque District. The bridges remain operative because all the approaches are protected. Congestion levels reduce from approximately 90% in the case that we saw before, P1, to 31%. And in this case, Sheikh Zayed Bridge is no longer a bottleneck. And adding to this case, P16, Khudairiyat Island. So in this case, we can see here that we have a reduction in congestion levels and connectivity remain the eastern islands remain disconnected. Now we will look into the case P1, 2, 3, 5, 8, and 9, which is to protect the entire northern and eastern part. In this case, eastern islands are connected to the mainland, all bridges are in operation, and we notice a significant improvement compared to only protecting the eastern island corridor that we saw before. So here we have the smallest decrease in the number of vehicles. To conclude, we find that it's critical to protect the approaches to bridges. One operational bridge only acts as a bottleneck. Also, when protecting a corridor that connects the main island to the eastern islands and the mainland, commuters are left with only one path to and from the CBD, and this creates again a different way and different kind of bottleneck, and generalized insights to other shorelines without running simulations. So we can have in other parts of the world similar suggestions. First is that areas with islands or peninsulas that are connected with bridges or tunnels, the entrances or approaches protection will decrease congestion levels, and protect links that create corridors. As we said before, this helps to prevent these different bottlenecks that may occur. This work has been submitted to the Journal of Infrastructure Systems as a case study. Thank you for your attention, and as I said, I welcome your comments or questions via email. Thank you very much.
I guess that makes the presentations for today, and thank you all for joining. For today's Young Researcher Day, I would especially like to express my appreciation to Rayan, Bingqing, and Rayan, who stayed up until so late to join our young research day. And for presenters, presentations have been really fascinating, and I'm really looking forward to working in collaboration with all of you. And also, I would like to thank to the evaluation panel for their participation among this so busy time. And lastly, thank you all for joining, and hope to meet you all in the next week. And thank you, and have a nice Friday.